Tim, you want to do the honors?
Yeah, I'm happy to. So yeah, welcome everybody. It's my pleasure to introduce Gaia Stucky de Quay, who is now a postdoc at Harvard. Gaia got degrees, her first degree at UCL, University College London, and then her PhD at Imperial College, following which she came to do a postdoc at UT. She joined my research group like 3 months after I started. So she was the first member of my research group besides me. And Gaia was here for, I guess, a little over 2 years. And yeah, like I said, has since moved to Harvard, where she's, I think it's like the Reginald Daly postdoctoral fellow, some named postdoctoral fellow. And then Gaia will be starting as a faculty member at MIT in January of next year. So 1 year at Harvard, and then followed by starting her own group at MIT. So we'll be looking forward to seeing the things that her group works on. Now we're going to hear about some work she did here when she was a postdoc at UT. So with that, I'll turn it over to Gaia.
Thanks, Tim. And yeah, thank you all for having me. And yeah, thanks for that introduction. I am very excited to be here talking about some of my work on landscape evolution. In general, I do it on planetary surfaces, but in particular, we're going to be looking at Mars here. And just before I start, I wanted to give a brief outline of what's coming up. So I'm going to take a couple of minutes to briefly describe my overarching research background and motivations, just for some context. Also, so I don't get branded as just a Mars person, because I do also like looking at other things. And then I'm going to describe this latest problem that I've been tackling with Tim while I was doing my postdoc at UT, after which I'm going to spend the rest of the time really digging deeper into some of this recent work that we've worked on together. And then I'm going to spend a little bit of time looking at future work that kind of developed naturally from all of this, and also the role that CPSH played in advancing that. And so with that, I guess I will just dive right in and start with the sort of big question that has driven my research direction up until now, which is broadly, how do landscapes such as, these two and very different planets that you can see here, how do they form, evolve, and decay over time? And one of the best ways to assess this is through the study of hydrological processes, which is what occurs in river systems. And the reason for that is that rivers essentially act as these kind of physical tape recorders, and we can use their morphology or their shape to quantitatively solve for controlling processes. So things such as tectonic activity, which is occurring in the subsurface, so that can be dynamic support or localized faulting, or even climate forcing, which is coupled to the hydrosphere from above. And so essentially we have these two opposing forces that are kind of modulating the surface, and they're both important in different ways. And like most problems, you can't solve for two things at once. So what you would do is to find, for example, a specific geological site where there's negligible or well-constrained tectonic activity to then solve for the climate signals and vice versa. And that's why Mars is such a great place, because there's little tectonism after a certain time in its history. And just as a quick overview, some of my past projects have focused on landscapes buried in the North Sea for my PhD. So they're 2 kilometers below the seabed. These were generated by mantle plume activity. I've looked at active glacially fed waterfalls in Icelandic canyons, as well as, of course, ancient water features on Mars. So although these span a broad range of spatial and temporal scales and consolidate all of these subdisciplines that I'm also interested in, the common thread throughout all of this work has always been, when looking at landscape morphology, namely hydrological features, what can they quantitatively tell us about the driving forces? And so there are several ways of tackling this question, but I found that, of course, a mix of techniques works best, ranging from numerical modeling to remote sensing, field work, and lab work. And again, I don't have infinite time to talk to you about all of these projects and approaches throughout the years. So what I'm going to do is to focus on my latest work, again, during my postdoc. And this was published as 2 separate studies with more on the way. And that'll hopefully give you an idea of how we can tackle this question of landscape evolution on a planet that we can't even access, and how we can deconvolve the important driving forces on these surfaces. So without further ado, I'm going to talk to you about some of this work on ancient surface processes on Mars. And so for those of you who aren't familiar with the red planet, which will probably be very few of you, I'll still take you through it. Today, Mars is an extremely cold and dead landscape. There's not much going on. However, it used to be quite dynamic in the past, so billions of years ago. And in fact, you've probably seen these headlines a million times where we keep discovering about water on Mars or ancient water on Mars. And maybe one of the best ways to make sense of this is to step all the way back to one of the very first sensationalist articles on the Mars surface. And I remember it was actually Tim who showed me this picture as well. And you can see here, you know, over 100 years ago, Percival Lowell decided to point a telescope at Mars. And so he was one of the first people to really notice evidence for water on a surface that is not the Earth. And so he mapped out these features, which he claimed pointed to an extensive network of channels, which he interpreted as artificial canals that were linking cities built by a very advanced civilization. So some big claims he was making there. But of course, we now know he didn't quite get the details right, but nevertheless, since then, vast amounts of evidence has kept coming in, and of course, with increasing resolution. So we know now that what he saw were these eroded valleys, and these used to host these fast-flowing rivers, and we call these valley networks, as well as deltas and fans. So this indicates that sediment was deposited in a large standing body of water. And that's just what we see with remote sensing. If we combine this with in situ rover data, we find equally compelling evidence at the centimeter scale, and that's in the form of pebbles and layered sediments, among others. But for now, we're going to focus on this part, the remote sensing data, because we're going to be looking at the large scale processes that are at play or were at play on Mars. And so for these geomorphic landforms, studies generally suggest that you needed long-lived runoff. So we're talking millions of years of liquid water, either as rainfall or snowmelt, to be able to form these. And so this burst of fluvial activity would have occurred sometime around here in Mars's history. So this is in billions of years. So sometime around 3.7 billion years is when we believe this happened. Sometime in between the Noachian and the Hesperian, which are these ages on Mars. And so that would require huge amounts of precipitation at this specific point in time. However, there's just one big problem, and that is that climate models for ancient Mars cannot recreate this amount of precipitation or liquid water stable on the surface for this amount of time, no matter how many knobs they turn in their models. It's simply too cold on Mars. And so that gives rise to this early Mars paradox, where you have climate scientists and geologists constantly trying to converge on an answer. And actually an editorial came out, which made it seem like it's a very hostile environment, but really much like the retaliation article that came out shortly after, it's not really a war. It's just, you know, we're simply trying to meet in the middle, trying to find a climate regime that satisfies both the models and the observations. And so one of the ways that we have reconciled both is by suggesting that during this wet period here, maybe it was not continuously wet and favorable the entire time, but instead it could have been comprised of smaller interspersed wet episodes, so something a bit more like this. But in order to verify or quantify the feasibility of the scenario and, you know, fix the rift between climate models and geologists, we need better constraints. And ultimately, what is really lacking is quantitative geomorphic constraints that can actually be used to test these models. And for example, if you look at valley networks that you can see here, these are great because these studies can give us cumulative amounts of water over the entire history, the geological timescale of the formation of the valleys, which is great, but it's not very useful on, at least for climate models. But on the other hand, studies of depositional channels have been used to calculate peak runoff or formative discharge. So this is more at the hourly or even daily timescale, which again is not really the correct timescale for validating global climate models. And so to really test for paleoclimate, there's this need for an intermediate, something to quantify a favorable climate event somewhere in between these two end member constraints. And this is where our latest work comes in. this region here is Arabia Terra on Mars. You can see that it's covered in these valley networks here, sculpting the surface, but also these paleolakes, which form naturally inside craters as there are depressions. And you can see that they flow into these craters. So now I'm going to show you how we can use these to quantitatively constrain water on the surface of Mars, and thus use that to probe the ancient climate. And the question that we are hoping to answer is, what was the intensity and duration of a favorable climate event? A favorable climate event being one of these peaks here. And so for the first part of the talk, we're going to focus on this first aspect, the intensity of the climate. Here's a brief outline of this first part, where I'm going to show you how we can combine remote sensing and mapping of the lakes with these standard hydrological equations to then derive precipitation across the Martian surface. So how can we go about measuring this for Mars? This is where I'm going to break things down a little bit. I'm going to use this really simple, maybe silly analogy, but it's really useful for wrapping your head around the kind of geomorphological record that exists on Mars, and broadly also explaining the methodology for this project. So anyways, imagine you own this big piece of land, and maybe you're a farmer, and you want to find out how much precipitation there is during a wet season in this field. The problem is you don't have much to work with, and actually all you have in your shed is a bunch of bathtubs for some reason. And they're all of different shapes and different sizes. So what you decide to do is to distribute all these bathtubs across your field with the idea that maybe they can be used to collect water. The only problem is that you're actually going to be gone for a long time. Maybe you're taking a really long vacation, but essentially you're fairly certain that by the time you come back, all the water will have evaporated after the wet season. So what can you do? Well, you have one secret weapon, which is a big pile of rubber duckies that came with all your bathtubs when you purchase them. What you do then is to place a single rubber ducky in each bathtub, something like this. And there you go. That's your setup. You then go away on your holiday. The wet season has now been and gone. You come back to check on your bathtubs and everything is dry as a bone again, as you expected. But what you find is that some of the rubber duckies are still inside the bathtub. However, for some of them, the ducky is now outside. And what you interpret is that for the duckies that are outside the bath, the precipitation must have been such that the entire bathtub filled up, overflowed, and then allowed the floating rubber ducky to escape. And conversely, all the contained duckies tell you that precipitation was not enough for the ducky to escape, which gives you a sort of binary classification of all the duckies. Then all you have to do is measure the sizes of the bathtubs, and voila, you have a new technique for figuring out how much precipitation your field received during a wet season in the past. But how does this apply to Mars? Well, as it turns out, we're looking at a very similar scenario, except instead of bathtubs and rubber duckies, we instead have basins and valleys. And instead of being gone for just one annual wet season on Earth, you're gone for much longer, maybe millions or billions of years. And that's long after the cessation of Mars's wet climate. This, for example, is a hydrologically closed basin on Mars. What this means is that all the valleys flow in, so these are the inlets going in here, highlighted in white, but there are no valleys that flow out, as you can see here. There are also hydrologically open basin lakes. So you can see here, there's also inlets going in the white arrow, but there's also an outlet canyon that was eroded here in the black arrow. And this occurred when the basin filled to the top, overflowed, and caused this big catastrophic flood that allowed the basin to drain. And to relate back to our farmer scenario, the presence of the outlet canyons are our escaped rubber duckies. And of course, the contained ones are our closed basin lakes on Mars. Unfortunately, we have a large database of about 100 ancient basins that are fed by valleys distributed all over Mars, of which about half of them are open and half of them are closed. And so by simply measuring their morphologies, we can combine this with what we term our hydrological balances, which I'll talk a bit about later, to then calculate what was the total amount of precipitation during a Mars ancient wet season. And for this, we need three key measurements. We need the lake area, the watershed area, which is the contributing area of the valleys going in, and then also the basin volume or the lake volume. And that's what those look like here, if we were to measure them. One thing that is important to note for open basin lakes is that the measured basin or lake volume here is actually a minimum lake volume, because this is the minimum amount that's needed for the lake to overflow, right? Because we know that it overflowed. Whereas for closed basin lakes, this volume we're measuring here is actually a maximum volume, because we know that the lake never overflowed because there is no outlet. Well, or the rubber ducky didn't escape, essentially. So those are the two end members we're dealing with, and that'll come back in later. And that's just to drill it in there. Perfect. So now I'm going to take you through these hydrological balances to see how we can actually derive an expression for precipitation using the measurements we've made. So when I use the term hydrological balance, all this refers to is this really standard set of conservation equations that just represents the amount of water that's entering and leaving a bounded hydrological system, whether that's a bathtub or a Mars basin. So in a simplified system, we have precipitation that is incident on a lake and its contributing watershed. So we assume that the water is just flowing on the surface, producing runoff, following topography, and ending up in the lake. That means we can then express the lake filling rate, or QL, which is a volume per time, as precipitation rate times the combined area. However, we're more interested in the total amounts, not the instantaneous rates. So what we do is to integrate this expression over some time period T, where T is a runoff episode equivalent to that wet season. And that gives us this expression, where the total lake volume is now the total precipitation times the combined area. And this term, PT, is what we want to solve for, the total precipitation over this time period. One important process we haven't mentioned, of course, is evaporation, and that could cause significant losses. And that would change our expression to something more like this, where you can have to account for the evaporation here. So to be able to find the total precipitation, we first need to constrain ET, or the total evaporation. One way to approach losses through evaporation is to consider what limits are provided by the lake basin morphologies themselves. What we can do is to take that earlier expression and the expression for the hydrological balance here, and then rearrange it so that we have now evaporation as a function of the precipitation. That means that each basin, whether it's open or closed, will have its own EP function, its own version of this, based on its geometry. And so, for example, here you have some EP, evaporation precipitation axes, and each basin, open or closed, will then map on to this graph like this, where each curve represents an individual lake. Blue is open, and then red are closed lakes. But now, if you remember what I said about the volumes, because the open basin lake volumes are a minimum, this line is actually an upper limit. So anything below it is permitted for each of the lines. On the other hand, for closed basin lakes, the volume is a maximum. So anything above this line is permitted. So it would look something like this. So these volumetric limits are basically turning this equation into an inequality. So how can we use this to give us a permitted evaporation total? Well, one way to evaluate this is by using the aridity index. This is generally defined as some ratio of precipitation over evaporation, or P over E. And because this is a log-log plot, any AI value or aridity index value plots as a straight line with a slope of 1. But as this line moves up, it becomes more arid. As this line moves down, it becomes more humid. So for example, on Earth, these are two values of aridity index. If you have a hyper-arid system, this is where your aridity index would plot. If you have a humid system, it would plot somewhere down here. What we then do is to essentially find what is the most arid scenario possible for these lakes to exist, or what is the lowest aridity index that allows for all of these open basin lakes to overflow on Mars. And the answer to that is given by this lowermost open basin lake in this really dark, thick blue line here. And so what this means is that this gives us a minimum aridity index that needs to be true for all of the open basin lakes to exist on Mars. So for example, if the aridity index was actually hyper-arid, or was this line here, everything below it wouldn't be able to exist. So all of these open basin lakes wouldn't be able to overflow. But if we've got at least this level of humidity here, all of these can exist. And that's how we find what the most arid scenario globally is for these systems. And so, as you can imagine, there is no limit on the humidity. They can be infinitely humid. So that means that we get this range of aridity, where basically the most arid scenario is a value of 0.6, this dotted line, which is around a semi-arid scenario on Earth, to infinitely humid, or where evaporation would be 0. And so we can then feed this aridity index back into our original equations to inform our hydrological balances. So this is the range of aridity index values. Using that simple relationship between evaporation and precipitation, we can feed that back in. And finally, we can solve for the minimum and maximum precipitation. And so remember, once again, we have these two n-member volume scenarios. Because the open basin lakes give us a minimum volume, we can only get a minimum precipitation from them. And so for that, we use our most humid scenario. And that really works to sort of push the minimum towards an even lower minimum. And on the other hand, for the closed basin lakes, we get a max volume, so we can only get a max precipitation. And so to push these to even being more liberal estimates, we use our most arid scenario plugged into that equation. And so what we're doing is to kind of push these limits out to get the most conservative minimums and the most liberal maximums. And employing these regimes, we get final expressions that look something like this, where we can now calculate the minimum and maximum total precipitation on Mars. So what do these results look like? One way to look at them is using a frequency distribution plot. Here in the x-axis, we have the total local precipitation calculated for each system. And in the y-axis, we have the total number of lakes in each bin. Remember that the precipitation is basically this integrated precipitation depth in meters over a kind of quasi-continuous runoff episode. And a conspicuous behavior we notice here is that open basin lakes and closed basin lakes have these distinct distributions with a very small amount of overlap. And this actually shows that our values are self-consistent, really, because remember that open basin lakes are a minimum and the closed basin lakes are a maximum. And so what this is saying is that the minimum is somewhere around 4 meters with some order of magnitude distribution globally, and the maximum is about 160 here. Again, it can be up to a few thousand in some of these basins. But importantly, these lakes are distributed across the entire planet. So what we end up with is this sort of spatial distribution of permitted precipitation on the surface of Mars globally. And one of the key implications of this work is that we now finally have these local values which can be directly tested against outputs of climate models. And that can give us specific quantitative constraints that models need to satisfy to be able to align with the geologic record. And so that really answers our first sub-question, the intensity. How much water was there in the early Mars climate? And if you want to read about that in more detail, this is the paper we published in Geology. But for the next part of the talk, we're going to focus on the temporal aspect. So how long could a favorable climate event last? And again, the structure is shown here briefly. We're going to be looking at the same geologic constraints, mapping of lakes, but we're going to integrate this with climate model data that exists for early Mars to then look at timescale as a function of space on Mars. And so I've shown you this map or something similar to it, where we've got all these lakes distributed on the surface. We're very lucky to have all of these. And although I talked about open and closed basins, there's also a third type of lake basin that we found, which we termed coupled lake system. And there's only 7 of these, so they're a little bit rare so far that we found. But they're really interesting. And the way they worked is that you basically got an open basin lake that is hydrologically connected to a closed basin lake. That is to say that the open basin lake breaches, the water flows straight into the closed basin lake, and that one doesn't breach. And this is an example of one of those on Mars. So you've got here the inlets flowing into the open basin lake. There's an outlet canyon here, which flows into this closed basin lake, which does not overflow itself, which are really exciting because you kind of see 2 processes happening in the same location. And I'll talk a bit more about why these are such important constraints. So first of all, when we talk about runoff or PT during an episode, called T, I just want to remind you that we're not talking about peak runoff or the cumulative runoff over the entirety of the lake lifetime, but it's simply a sort of an amount fed into a lake during a single quasi-continuous episode. And so to relate back to the plot, it's one of these events, right? And so we can think about this plot more dynamically. Looking here, imagine we have some sort of oscillating climate, which produces runoff events over time. If the events are not long enough or intense enough, they will not cause an open basin lake to breach. However, if there's a single event that is long or intense enough, that will cause the open basin lake to breach. And this threshold event, that's what characterizes the total minimum precipitation depth for that runoff episode. And this episode is defined as our runoff episode T. And notice that this does not provide us any information on the events before or after that could have happened. For closed basin lakes, the idea is similar, but in this scenario, there is never an event that is long or intense enough to ever breach the lake. And that gives us information on the maximum amount of PT that could have occurred again over some T. And so for a coupled system, which contains both an open basin lake and a closed basin lake, we know that T and PT are the same because they're hydrologically connected. They're in the same place. They're spatially and temporally coincident. So that should allow us to investigate their hydrology and timescales in more depth. One way to look at this is to examine how the lake volumes of both these lakes vary over time. So how does V change as a function of time? I won't delve into the maths, but I just want to show you that they exist. I would much rather go through this graphically as it makes a bit more sense, but I just want to prove to you that there is some reason behind all the lines I'm going to show you. Here, we're going to be looking at the x-axis, which is some dimensionless time for now, where 1 is where the breach occurs. And then in the y-axis, that's just the lake volumes here of both, in red, the closed basin lake, and the blue, the open basin lake. And that's where the breach occurs. So this is a very simple model. I'll take you through all the stages. Firstly, before any breaching occurs, the open basin lake will essentially fill up with water proportional to the size of its watershed, as does the closed basin lake. Once the open basin lake then reaches its maximum volume that the basin can hold, of course, it's going to overflow and cause a breach that then results in a canyon being eroded. And as the canyon erodes, it loses a bit of water, but then it retains the same volume as any water that comes in then leaves the system. However, once this happens, this water then gets transferred downstream through the outlet into the closed basin lake. Also, after this, the closed basin lake has now acquired both of the watersheds. So it's going to increase in volume at a much higher rate because now all the water that is falling into this entire system goes into the closed basin lake. But we know that the lake never overflows. So runoff production cannot continue, no matter how fast it goes, it cannot continue past this point where the lake would reach its maximum volume. So what we end up with is this sort of defined range of permitted timescales you see here in gray, which tells us that runoff had to be this discrete event. And for example, for this system, runoff could have occurred for about 44% longer than it initially took to fill up the open basin lake. And so these relationships are interesting because they give us an idea of the lake timescales, at least with regards to filling and breaching and subsequent overflowing. But how can we go about actually quantifying the duration of a runoff episode T? Here, I'm going to show you a sort of simple way to tackle this. First, we have our total local precipitation, PT, for each coupled system. So this gives us a range of water depths in meters. Second, another constraint we have is precipitation rates derived from these global climate models. There are several of them. This is the one by Robin Wordsworth in 2015. It's just a spatial distribution of rainfall rates in meters per year. And so quite simply, if we have a precipitation total and a model precipitation rate, we can then use these two to solve for a total episode timescale T using this relationship very simply, for example, in years. And so suppose we have this global distribution of precipitation, such as this one here. What we first need to do is to actually find the precipitation rates within our paleolake basins to get an average runoff rate just for each individual basin. And again, there's several of these different climate models, so we can do this for all the different models, for all their different scenarios. which there are several of, and I'll take you through some of them after. But just to show you, the technique here is basically to just calculate the average within this basin. So this one is just under a meter per year, and this one is half a meter per year for Robin Wordsworth model here. So anyways, now each basin has a total precipitation and also a modeled average precipitation rate. And remember that there's a range of permitted timescales for each individual coupled system, because we need to be able to breach it, but we can't flow too much that it overflows downstream. And so currently we have a total of 7 coupled systems. So depending on the morphologies of each system, we will then have different ranges of permitted timescales for each of them. And so essentially what we're trying to do here is to build a histogram of all these permitted timescales. So if you imagine a time that is somewhere here, it would only fit one of these systems, but a timescale that is somewhere here would fit several of these systems, almost all of them. And because we've now got precipitation rate, we can turn this into an absolute time and make this histogram, which looks something like this. And I'll take you through this. Essentially here, the x-axis is the duration of the episode in years, and the y-axis tells us how many of these 7 coupled systems are satisfied by this time bin. And so, for example, here, a episode duration of 10 years would only satisfy 1 coupled system, but an episode duration of 100 to 200 years satisfies 5 out of the total 7 systems. And this makes this the most permissible or most probable time bin, at least for this model. But not only can you do this for a single scenario, for example, Wordsworth has rain and then models of snow, and we can compare those, but also different models altogether. So Kamada, for example, look at how atmospheric pressure changes the runoff, and we can see how that in turn changes the episode durations. We also have a model by Scott, who looks at how the global equivalent layer of water changes the climate. So here we've got 10 meters up to half a kilometer of water covering the surface. That doesn't change it very much. And then also other models that are a bit more discrete. So Catherine in 2019 has a model where essentially an impactor hits Mars and generates a runoff producing climate. And you get different runoffs depending on if the impactor was bigger, 100 kilometers, or smaller, 50 kilometers. And I don't have time to talk about all the individual timescales and how they change the runoffs and the times and the specific timescales, but I just wanted to show you that what all these look like together, and mainly so that I can point out some key observations. First, you'll notice that the most permissible timescales seem to most commonly lie between 100 to 10,000 years, and that's for a single runoff episode. And then I'll remind you that you actually need many of these episodes to be able to carve the really deep valleys that flow into these coupled systems, which means you need several of these cycles to be able to match the observations we see. Second, there's actually no timescale that satisfies more than 5 coupled systems out of the total of 7, which is still a good achievement. And it could mean either that there wasn't a single T or timescale episode that is valid for all of the coupled systems. It could have happened in different episodes or for different durations, or there is yet more space to explore other models that could satisfy more systems. And so how does all of this feed back into our current understanding of the Mars climate? As I mentioned, we have some idea that this climate may consist of this oscillating wet episodes you can see here. And the main constraints we had previously were things like, what is the peak runoff? How high could this peak go at any given instant? Or what is the total water volume? So adding up all the areas of these rectangles. And you'll note that both of these are either maximums or minimums. And although they are valuable, it's not clear how they can directly help us resolve the structure of this broader climate framework on Mars. However, in this work, I've just shown you that we quantified the precipitation total for an episode, and also the duration of an episode. And then we have a grant and review that would tackle the total timescales permitted, and I'll talk a little bit about that in a second, and future plans for analyses into intermittency, possible variability, and crucially, all of this is needed to shed light into the forcing mechanism, what is actually dictating this quasi-cyclical climate variability, and also potentially on its eventual decline. And you have to remember that Mars is the only planet we know of that has undergone global and irreversible climate change. So of course, this has important implications for understanding climate change at a planetary scale, and for understanding it on Earth too. So anyways, to move on from here, I just wanted to spend the last few minutes talking about future work, both in the context of the knowledge gaps I've just shown you here, but also more importantly, to highlight the importance of the CPSH Seed Grant, which is, was really critical towards enabling me, enabling this work to be carried on when I was at UT and to tackle a lot of these important questions. And so these are the two papers that were published from that. And so I'm just going to talk a bit more about this future work here. So anyways, during my postdoc with Tim, we designed this really neat proposal that you can see here, spatio-temporal paleoclimate constraints from coupled lake systems on Mars. It was meant to be submitted to the NASA Mars Data Analysis Program, or MDAP. And as you can see from the title, the objective was to characterize the Mars climate, much like everything I've talked about here, but specifically focusing on these coupled lake systems. So that was the idea of this proposal, to really dig into these landforms. And this was submitted in 2019 initially. If I just go back, this is actually a screenshot of the objectives, which is essentially what I just told you guys about in that graphic. But yeah, so it focuses on these coupled systems. You saw that we only found 7 so far, and being able to look at it in higher resolution and really try and find some more of these would be really interesting. I mean, these key systems, they give us closed boundaries on water amounts, which is, on Mars, that's so rare. You usually get a minimum or a maximum amount. So we really wanted to capitalize on these landforms. And so, not only the work that I've outlined before that we would do at higher resolution and find other systems for, but also there's a lot of work outlined in the MDAP where we'd be looking more closely at sediment volumes and looking at the morphology of the valleys that are feeding these systems. So a lot of different techniques to complement our work that I've just shown here to answer a couple more of those questions of the Mars climate variability. And what then happened, of course, was after our first submission, we got good reviews, but of course the reviewers picked up on at least one important weakness at the time, which was looking at groundwater. So how did groundwater affect our results? And so we addressed this in multiple layers of resilience. We kind of went over the top there, but first for the regions that have the same aridity index as ours, we looked at data on Earth, and we found that, well, as you get more arid, groundwater contribution becomes less important. And so if we're talking about an aridity index that's around here on Mars, you'd expect groundwater contribution to be minimal. But even so, we added calculations and considerations for groundwater into our equations. We included large losses, so about 50%. Imagine 50% of the lake gets lost if you've got really fractured basalts, and that's something that we see in fractured basalts in Idaho. So we put that in, and even then, this only changes our value by very little, again, because so much of the losses are through evaporation. We also then looked at what if we lose water in the watershed as well. So about only half of the precipitation turns into runoff. That also only changes our maximum by a bit and our minimums by a bit. Like everything remains within the same order of magnitude. So again, evaporation processes are the main drivers of where the water is going here. But anyways, we fixed all this up. We resubmitted our proposal, and this was our preliminary schedule that we submitted to CPSH. Collect pilot data, check all the data that I showed you now, the terrestrial data, and check that we're addressing this in the right way. Restructure the proposal, make it even more exciting so that people get excited about coupled systems. And then we also discussed the possibility of another proposal that could tackle other questions. And of course, I'm happy to say that despite this all being at the peak of COVID, we were able to accomplish all of this. I'm also very happy to say that the MDAP was selected last year, which is great. So we're in the process of having that transferred to MIT. And yeah, if I'm going to start as a faculty. So if you know of any postdocs who would love to work on an extension of this work and everything that I mentioned before, or if that's you, please do reach out, because I'd love to have a postdoc working on this starting at the end of this year or next year. And then for the third part, actually, we had planned to submit something for habitable worlds. That's actually the only NASA program that's related to my work that I haven't submitted to. I've submitted to solar system workings. We've submitted a P-STAR, which is the Earth analog work. And then we're also working on a discovery mission proposal. So a lot of these will answer extremely analogous questions, very close to everything I've just outlined in this talk. So, the intermittency, the length of these fluvial timescales. So there's a lot going on in terms of being able to shine a bit more light in those questions. So I'm really excited about all of that. And, just wanted to thank the CPSH because they truly enabled all of this. And it's a tough time in a postdoc when you have to patch up those holes between postdocs and between faculty, but this really helped everything go extremely smoothly. So that was really great. And so with that, I just wanted to end my presentation. A quick summary. We looked at these paleolakes. They're really exciting because just by looking at their morphology through remote sensing, you can infer precipitation and aridity regimes. So, a few meters to a few 100 meters, anywhere between that, and then a semi-arid regime on Mars is what we found. We can also combine that with climate data to then look at the amount of time it would take for these episodes. So anywhere between 100 years to 10,000 years, and you require several of these episodes. And then I talked a bit about my future work, and hopefully you'll see that sometime soon as well. And yeah, shout out to CPSH for helping to make that happen. And thank you.
We have some applause. We have some time for questions for those who'd like. I do have one, but I would yield to anybody else. Let me ask mine. You talk about evaporation. Does anything change if the surface is not liquid in your assumptions, like if it freezes?
If it freezes, that would be lumped into being a sort of intermittent episode where fluvial activity wouldn't happen, I guess, which is just baked into our assumptions of intermittency, really. But I mean, the lake has to be liquid because the lake is overflowing, or at least the bulk of the lake has to be liquid because that potential energy has to fill up in the lake to then overflow and carve an enormous canyon that flows out of the lake. So the entire system can't be frozen. It can freeze over temporarily for sure, but the amounts of water flowing in, the runoff flowing in has to be liquid, causing those valley networks to form, if that makes sense. Does that answer your question? Or no?
Well, but you had assumptions about, or statements about evaporation. And evaporation from an ice-covered lake is different than from that's a sublimation. It's different than from a liquid lake.
That is true, but our evaporation isn't based on any process. It's just based on the observation of what can physically go in, what is the input and the output of the system. And so we're just reporting that ratio to you. We're not telling you whether it was liquid or ice covered at all. We're just finding that the ratio of what's going into the lake and what can leave the lake is this 0.26. Whether it's ice covered or not, I can't say. But then, of course, that would, if you want to infer the, relative to the Earth, the aridity index, of course, that would change things a bit. But that's just the ratio of what's going in and out of the lake, because it's just P over E, or P over a question mark.
Okay. Sean has raised his hand.
Yeah, so I had a different question, but actually maybe I want to first ask a follow-up on David's question. So are there polar locations with high aridity where you could have seasonality? Help explain, kind of following up this question. What if it's frozen part of the time and then your runoff are in, like an Alaska setting where you get all of it in the spring,
Yes.
and then it steadily returns back to dry and refreezes, Yeah,
of course. So the lake catalog is constrained to not polar regions. So I think we look at a maximum plus or minus 30 degrees to minimize that effect, both geomorphologically and of course in the process that you mentioned. But again, you know, whether the process that is stopping the runoff is very high aridity, so things are just dry and there's nothing flowing, or everything is frozen and nothing is flowing, that would again be kind of counted into the event. Essentially what we're saying is that runoff had to start to be able to, runoff started at some point and it had to breach that lake and it had to overflow. What happened in between any variability, the smaller scale variability between being able to fill up a lake but not fill up the next lake, that's, you know, that's somewhere in there that we can't really deconvolve with the data that we have. But absolutely there can be variability, whether it's through aridity or through glaciation, but we don't have the ability to resolve that. But it can't have stopped so completely that you weren't able to first breach that first lake in the first place, right? It just stopped at some point.
Yeah, so I guess my that's interesting. So my second question is the closed basin lakes, because you don't have the original crater rims, then the value you have now isn't really your maximum, right? It's the maximum you can account for at the moment, but it could have been far more.
It could have been even
It
more.
should have been, right?
Yes. We have, I mean, a lot of them have proper rim. The rim isn't completely gone, so they do have rims. We could potentially have a look at how much of that could have disappeared and how much that could affect the total volume of the closed basin lake.
I mean, I guess I'm partly thinking about this because we know that these are smooth morphologies because they're missing the morphologic features they should have for their size, right?
Yes.
So either they're infilled or they're eroded. Either way, the rim is probably reduced in relief.
Yes.
And thus the value is probably originally a larger value for the size of the crater than that. I mean, it's more than your maximum, right?
Systematically, that could also be true for the open basin lakes then. So that would
potentially, yes. Yeah.
Yeah, but yeah, absolutely. That's actually something I didn't distinctly consider, but yeah, absolutely. I mean, we tried we did absolutely, you know, reconstruct it, especially for the open basin lake, you know, removing that outlet, what was the basin without that outlet, but that takes into account, you know, what is the highest point in the rim that we can find. But of course, like you said, even if it's the highest point, it doesn't necessarily correspond to what it could have been before. But yeah.
But you know which direction it went, right? It only should have been more relief, not less, right?
Yeah.
So that's
of course. Yeah, of course.
Yeah. Anyway, great talk. Thanks.
Thank you.
Other questions? You can just, if you do, chime in. Okay. So, Gaia, thank you very much. Very much appreciate that.
Thank you. Thank you all for having me.
We're going to hopefully post this and see y'all in a few weeks. I'm not exactly sure when.
Well, next week we have our executive committee meeting, right? So actually next week we don't have anything because we're at LPSC. Right. So then the week after we have our week after spring break, so we canceled that. So then the week after that is the next one. Yeah.
Okay. Well.
All
right.
Thank you, everyone.
Thank you much. Appreciate it.
Yeah. Thanks very much. That was a great talk.
Thanks.